Okay, so thank you very much. I would like to thank organizers for such a nice conference here. Also, school was very nice. And so what I'm going to talk about laser cooling and trapping of rubidium at this 5s half to 6p 3/2 blue transition. I'm from IIT Guwahati, and this is the beautiful campus you can see. We are having, this campus is located on the bank of this Brahmaputra river. These are my PhD students who have conducted this experiment. Few are missing who are participating in the ytterbium experiment. If time will allow, I will also talk about our recent effort towards ytterbium cooling and trapping. So let me tell you what is the global scenario of laser cooling and trapping of atoms, what kind of elements which are being cooled. So this is the periodic table, and all the elements which are written in the red font has been cooled, okay? This column, I think cooling has been, now there is no further news from this column. I do not see any news. Mainly news are coming from this column, except this francium. And also the news are coming from this dysprosium and ytterbium. For the quantum computation, which is also our effort, future plan, mainly news, it's rubidium and cesium are being used, mainly rubidium. What we are also planning to do the quantum computation using rubidium and ytterbium at IIT Guwahati. And there are some recent effort on international level also for the quantum computation using strontium and ytterbium, showing the superiority of these ytterbium and strontium over rubidium. Okay, so I will discuss all this. Let's see how much time allows me to do it. Okay, so before I discuss this laser cooling, I would like to talk about the reason behind we are doing this laser cooling of rubidium using 420 nanometer. Okay. Yesterday there was talk by Arijit about clock and all. Recently we proposed this scheme of two-photon resonance detection in the lambda system using transient effect, okay, in the transient regime, not in the steady state regime. In the steady state regime, if you do measurement on EIT, the line width of this EIT window scales as an optical thickness like this. It scales as under root B naught. Okay. So you are getting narrower line width of the EIT in the steady state, but it only scales as under root B. But what we are going to talk about, some scheme in which it will scale as 1 by B. Okay, B is the optical thickness. And what we are utilizing here is this interferometric method. Okay, so let me introduce what is this interferometric method. Is Homodyne detection, where we have two lights, okay, and then we divide these two lights into two paths, and then they interfere. So any kind of perturbation happens in one path is detected, okay, because this interferometry is very sensitive because the wavelength is very small. We are also going to use similar idea, and in our idea, these two lights are flash and slow light. Okay, so these are not physically separated two paths, but these are two sources generated from the atom. Okay, so I will discuss about what is flash and what is slow light quickly. So I start with very simple idea that if you shine a light on a atomic cloud, and if you are having an optical thickness of this atomic cloud, the outcome, the intensity will be attenuated, and which is given by this formula, which is very well known. So what is the idea is that in the forward direction, when we shine the light on a cloud, there is attenuation. Okay, and why does this attenuation happen? Well, because the light comes here, and we know from Huygens principle that each and every atom gives rise to secondary wavelets. So each and individual atom you can treat as a dipole, then they also starts emitting light. Now the question is, the incident light and the scattered light, are they in phase or not? And answer is no, they are out of phase, and then they destructively interfere with each other. So as an outcome, you see that intensity of this transmitted beam is less, right? Because they are destructively interfering with each other. So there are incident beam, and then there are scattered lights from this photon, from these atoms. Okay, in order to convince you that they are going to destructively interfere, I don't need hi-fi things. It's only 10+2 subject. So we consider a dipole here, and we are having an incident light, and we know that dipole oscillates with this incident light, and the phase of this oscillating dipole happens to be this much. Okay, so if we are at the resonance, the phase of this oscillating dipole will be out of phase by pi/2. Okay. So we are having incident light, this dipole will start oscillating, the phase of this dipole will be pi/2. So light which is here will be pi/2 out of phase. However, no, if you go beyond this dipole, there is going to be another pi/2 phase, and that's called Ghosh phase, which was discussed yesterday by Professor Pandey. So overall, we get pi phase difference between incident light and the scattered light. So they are destructively interfering with each other. Now, another important point is transient time response of the system or dipole happens to be gamma, where gamma is the damping rate of this spring. If you talk classically completely, semi-classically, we know that gamma is the damping rate of this excited state. So any kind of, for example, you are doing amplitude modulation, you are doing very, very fast, more than gamma, atom will not respond. Okay. Okay, so this is the key point to utilize this. Okay. So what happens? The another important point is, so all these atoms, okay, they are not at one point, but they are spatially separated. But in the forward direction, all the scattered scattered field will be in the phase. Okay, if you talk about in this direction, they are going to act coherently, cooperatively. Okay, this is clear from this figure. Okay, if you are talking about scattering in this direction, of course there is going to be a phase difference between this atom and this atom. However, in this direction, there is not going to be any phase difference between the scattered light emitted by these two atoms. Okay. So now what we do here, we shine the light. You know, we say that, okay, we are having very large optical thickness. So you see that scattered light and incident light, they are having almost equal amplitude. They are destructively interfering. So transmitted field will be almost zero in the steady state. But what I do is, I suddenly turn off the light, incident light. If I suddenly turn off the incident light, the incident beam E naught will be zero, and only scattering field will be there. Right? In order to, this scattering field will not die immediately. It will die in the time scale of gamma. Okay? So you can see that if I turn off here, for example here, there is still light because scattering field has not died completely. Okay, so this is called flash. Similarly, here when we are shining the light on the atom, if you see it properly in the time in the time domain, immediately you are not seeing the dark spot. Initially, it will be all the field will be transmitted because you need gamma time. You know, you need some time, which is gamma, to build up the scattering field. So in gamma time scale, scattering fields build up, and then it kills the incident field, and then you are having transmitted field zero. Cool. So this is called flash. Okay, this is called flash. So I hope I have explained one source of light which is being used for this interferometric technique. Another field is very well known, that's slow light. Okay, and because of this EIT, if you are shining some light, you know, pulse, it is going to be slow because of the dispersion created by this EIT. Okay, and we know that this group velocity is given by this, and if you calculate the time delay, you know, time delay happens as B naught, which is optical thickness of this medium, and this is the coupling frequency of this laser. We have done all this calculation in this approximation that ground state decoherence rate is quite small compared to the coupling field. Okay, so now there is interference happening here, that when we shine here, you know, we see kind of flash here because scattering field is building up. Here, what is happening, that we are having a slow light. Here we are turning off the laser. Okay, we are giving a pulse, like a square pulse. So here we are turning off the light, and you see that intensity is more than around 3 times. Okay, so because we are seeing around 4 times is because there is a scattering field, there is flash, and then there is slow light. So if they are in the phase, 1 plus 1 is 2, intensity square is 4 times. Okay, so this is what we are seeing, right? So If you want to hurt somebody by laser intensity, okay, it's recorded, right? Oh, okay, sorry. So if you want to hurt somebody by laser intensity in self-defense, okay, okay, you have to turn off the laser. He will be damaged more. Okay, so that's the idea. Okay, so here we are turning off the laser, and then you are seeing 4 times intensity than the incident intensity. Okay, and this is because interference between slow light and flash. When we are at 2-photon resonance, there is no dispersion of the slow light. The flash is having pi phase shift, so we see minimum intensity when we are turning off. But when it is pi, the dispersion by this atom is around pi, then we see around 4 times. Okay, we don't get exactly 4 times because as we are moving from the 2-photon resonance, there is absorption happening of this slow light, and then we don't get really 4 times. So this is the way we want to do this measurement of the 2-photon resonance measurement. And the idea is that this will scale, this resonance sharpness will scale as 1 by B naught, not 1 by under root B naught, which happens in the steady state case. Okay, so this is the advantage. Also, this is cooperative. Okay, so I will move little bit faster because I don't know how much time I have. Okay, so only 13 minutes. Okay, so this is also important that, when you want to conduct this kind of experiment, I said suddenly, there is no sudden in physics, right? Suddenly means we have to be very fast, faster than B naught gamma, okay, where B naught is the optical thickness. So if we are planning to use B naught like 350, or for example, even 50, typical in rubidium, the lifetime of, gamma is around 26 nanosecond. We have to turn off very, very fast, okay? So this experiment requires some fast switching kind of circuit we need.
Yeah, but B naught times 20 nanoseconds is something like microseconds. It's not that far.
No, B naught by 20. Gamma by B naught.
I see.
Okay. So it has to be 26 nanosecond divided by 50 is the time we need to turn off.
But is that feasible, like picosecond?
Yeah, it is feasible. If you use EOM, for example, you can turn off. Okay. So we are in the process of doing this. We are planning to use EOM. It is not necessary that I have to turn off this incident beam. If I just simply rotate the phase of this incident beam, then also it will work. Okay. And we know that rotating phase is much easier with EOM. And you can typically get EOM with like 9 gigahertz, 10 gigahertz bandwidth. So it's quite feasible. The only thing is we have to generate this pulse, okay, which does the job. So we are looking for this possibility, okay. But another solution is, let's use some narrow line width, okay. And that's how we came to this idea that let's better to use some other transition which is having narrow line width. Okay, gamma is higher. Sorry, gamma is lower. Okay, and we know that if we are talking about the transition which is having large principal quantum number difference, then this dipole matrix element goes down, right? Because the overlap of the wave function is going to go down. Our expert Vijay Sahu knows about all these things very well. So that's how we contacted him in the beginning when we were planning to conduct this experiment. We talked to him. I wrote an email. So, and then we also wanted to do this laser cooling at this transition, this 420 transition. This 420 is quite familiar number, in Indian context, right? Yeah. So I mean, people are given punishment for doing fraud. Okay, so this is not the reason we are doing. Okay, this 420 nanometer cooling. This is because it is having narrow transition line width. So this is the commonly used energy level for rubidium for cooling and trapping. Here is the cooling for 420 nanometer. Okay, these are the energy levels, and again we calculated all these. How does this decay, and so on. There was some discussion going on when Arijit was giving talk that what will be the good idea, how does this decay and so on. So you can get this number that how does all these individual levels decay to different levels. We utilize this paper to calculate all these decay, and again it was suggested by Professor B.K. Sahu. All these things, all these papers. So what is the point is that this 420 nanometer, the total line width of this 420 is around 1.2 megahertz or 1.3 megahertz. Okay, but majority is decaying. It's not closed transition. Majority are decaying here. It's if 0.32 is only decaying here. And we were quite nervous that this laser cooling will not work because we were using repumper, 780 nanometer repumper, and then 420 nanometer cooling. And if branching is too poor, there'll be more heating effect because of the repumper rather than cooling. Okay, but somehow it worked well. I mean, that is a bit surprising, but this is the only field where experiment works better than theory. Okay, that's what I feel sometimes. Most of the time things will not work, but when it will work better than prediction. Okay, so it has worked, and also we were quite worried about what will happen with ionization and so on, because if you consider this 420 nanometer, the atoms are being ionized and so on. So overall it worked. Okay, so let's see. What was the main challenge was the spectroscopy. Okay, so we tried direct spectroscopy. We had to do heating of the cell, and this is our heating mechanism. We had to apply the magnetic field and so on. People have done this direct absolute frequency measurement, but I mean, they had some kind of blue enhanced photo detector, which we don't have. So we did something different. Okay, we also tried. We got the spectrum, but there was coating happening all the time on the window, and then we said, okay, let's not worry. We started working on this kind of double resonance spectroscopy, where we monitor the probe absorption in the presence of 420 nanometer. Okay, and that there is transfer of coherence between these two. There is optical pumping happening to another state, and then in this way we find the spectrum. Okay, that whenever this control laser is coming to the resonance, there is going to be a transparency of 420, or in this case, enhanced absorption of this 780 nanometer. Okay, so we utilize this, but unfortunately, Okay, we also did some hyperfine measurement for this, and then we got this result. And here Professor Vasant Natarajan was helping for this experiment. But what was the problem was with double resonance, that we were getting this large line width. Okay, it's around 30 megahertz, and well, we are targeting about 1.4 megahertz line width transition. That was quite annoying. But what we did is, we did something like this. We put another counter propagating control laser here, and this another counter propagating laser. Okay, and then we found that we can get okay, so this is a lot of detail. I don't want to go in detail. The crux of matter on bottom line is, if we put spare here, extra laser here, counter propagating this blue laser and counter propagating 780 laser, we split this EIT and EA spectrum, and then we get some kind of narrower line width. We typically got like 8 megahertz. Okay, so for example, here is the case where we couldn't resolve. In the case of 85, these hyperfine levels are too close, we couldn't resolve. But when we put this kind of scheme, we could resolve these things. Okay, so for example, this is 10 megahertz away, 20 megahertz away. We were able to resolve these hyperfine levels. Okay, so certainly it was working for us to resolve these hyperfine levels, and then we are locking these our rubidium 420 nanometer laser at this transition. Okay, so this is our MOT scheme. Repumper is still there on the this 780, and MOT is on this. And then this is our scheme where we co-propagate using dichroic mirror, and we are having dual wave plate. This is our chamber, and this is our spectroscopy. In the same cell, we are doing spectroscopy of the MOT and repumper. This is a bit congested space-wise because, okay, but we don't have other option because we don't have any other rubidium cell. So we are doing like this. And then in the other cell, we are doing a spectroscopy of this 420. And then this is our setup. And this is the combination of blue and red MOT. So what initially we did that in order to check whether things are working or not, in two arms, we put 780, and in one arm, we 420. And then we saw that, oh, MOT is coming. Okay, so that was a good sign to go ahead. And this is our red MOT with loading time 10 to the power 8 atoms typically. In order to transfer this red MOT to blue MOT, we typically simply remove this shutter. And we were doing all this using this removal because at that time we didn't have AOMs and all. So we were just simply on the focus, we were just cutting the 780 nanometer laser. And then we were doing all this. But unfortunately, this shutter is quite jittery. Okay, so we don't get a very reproducible kind of result. And then there was lockdown, and after that, in between, we got the AOM, and then we could do the measurement, and these are the results. So bottom line is we got temperature up to around 50 to 60 microkelvin. Typically in MOT without Sisyphus cooling, polarization gradient cooling, we were getting temperature around 500 microkelvin, while this one we were getting around 50 microkelvin, which is quite useful. Okay, people can ask, oh, why don't you go for Sisyphus cooling? But look, for Sisyphus cooling, you have to turn off the magnetic field, and then atoms flies in between. So if you want to load in ODT, it's not good. Okay, so in that sense, this is quite good because you don't have to turn off the MOT and then directly load the atoms in ODT. And this is how this blue MOT is changing the size with time. So typically, cooling happens very fast. Okay, cooling happens in millisecond. In 1 millisecond, you are cooled. But the spatially squeezing happens a bit slow, And typically in this case, we were squeezing in around 15-20 milliseconds. The atoms were settled in their position. And this is the characterization and so on. And I will not talk about ytterbium. Okay, so I will talk when we will meet next time. So thank you very much for your kind attention.
Questions?
You can get like 20 nanoseconds.
No, AOM, I am saying.
AOM.
Yeah.
AOM also. AOM we have.
AOM 25 nanosecond you can get. 25 nanosecond. If you focus the beam, you can.
Yeah, we have also tried. We also focus the beam. Which AOM you are using then?
I'm using from Primrose. Okay. So what matters is the caustic velocity which is going through the crystal. So Primrose I have used, and then there is another AOM from this.
Actually, time scale I'm considering.
I think 25 nanosecond is a reasonable time.
EOM you are hoping it will better than that?
EOM happens to be much faster, yes. The EOM you can buy from EOE space at bandwidth of 10 gigahertz.
We have already.
Okay. So next question.
Hello, yeah. So I have a little curious question. So you showed that periodic table. Yes, and so thulium was not in red. And I know that there was a lot of interest in exploring rare earth iron doped crystals. With experiments, in your introductory slide, yeah. So there was a lot of interest in all these rare earth iron doped crystal. For example, thulium 3+. Thulium is next to ytterbium.
Okay.
Yeah. So maybe can you comment on that? What happened to those experiments? Because there were many groups who were exploring.
Okay.
Not many, maybe, but at least a few very ambitious groups who were exploring. And these were very beautiful systems because they had very narrow, like natural line widths within a broad this thing. And there were experiments on spectral hole burning and stuff like that. Okay. And there was also this belief at some point of time that maybe so
first of all, then I will correct because I was not aware, and then I will look at it because it is close to ytterbium.
But just the thulium atom, you mean? And what about these rare earth iron doped crystals? Because they are solid state systems. No, not for precision, maybe. So I'm not talking about precision measurement.
Yeah, it may be available, but as far as I know, there is a group in Switzerland who is trying to make atomic clock using thulium atom.
Okay. So maybe for precision measurements, there are. Yes. But there was a lot of interest, I think, because of the scalability, the D. Vincenzo criteria for in like quantum information and computation, right? There was this point about scalability. So, if you target a solid state system, maybe you'll get many, many atoms of the same type, right? So I think in that sense, rare earth iron doped crystals were very famous, or they became popular at some time. But
in that sense, I was listening this talk by which group? Rubidium experiment, Lukin and other Safman. So Safman is doing this one, with showing a lot of advantage of over rubidium and cesium. So he is setting up the lab.
Okay.
On that. So experimentally, it might be because the way you are setting up the experiment with the two path like a Mach-Zehnder, it might be advantageous also because you may avoid any part of the incoherent beam coming in that direction if you look for the backscattering. I don't know, maybe there are details.
Okay, I will look for it. Okay, thank you.
Work. Yeah, so I was a little confused about the two-photon transition that finally you're planning to do. That's like the blue and the red mot together, like that V system that you're showing. Like what gamma you're thinking?
Two-photon, no. Two-photon I want to do using lambda system. This blue cooling I'm doing to increase the optical thickness and in order to make the sample more cooler and cooler. That's it.
I see, to go to lower temperatures.
Yes.
Any other question? Oh, okay, yeah. Thank you. Thank you.